Assalamualaikum and good day. So my name is Daniel. So today I would like to present a comprehensive verification of our circuit design for simulation 1. We will look at how our hand calculated values stack up against an industry standard PSP simulation, specifically focusing on validation of law of conservation of energy. So first and foremost, we tackle the circuit using manual mathematical analysis. By applying fundamental circuit laws, we determine the exact voltage and current for every single component. From there, we calculate the power. Our hand calculation revealed a total power dissipation of exactly 1740 watt, with 3 sources supplying energy and 3 resistors absorbing it. So next, to verify these manual findings, we model the identical circuit in PSPice. We execute a DC bias point simulation to capture the behavior of the system under steady-state conditions. The software directly measures the power throughout of each individual component, providing an unbiased algorithmic baseline for our manual work. Now, moving on to our comparison. If you look at comparison table on this slide, you will see an exceptional alignment between the two methods. For instance, our manual calculation placed at 1740 watt and PSPi hit exactly the same 1740 watt. Across the board, every single component matched its simulated counterpart almost perfectly. After comparison, this brings us to our discussion. Crucially, both methods perfectly satisfy Cayley's theorem, meaning the total power supplied equals the total power absorbed at exactly 1740 watt. You might notice microscopic differences like 980 watt versus 918.6 watt on the source V2. This is simply due to minor decimal rounding in PSPi's current solver. It does not compromise the integrity of our inner. So in conclusion, the simulation successfully validates our manual design approach. The overlapping results prove that our mathematical model is highly accurate and dependable. Thank you for your time.
Good day everyone. Today, I am presenting the verification of a single loop circuit containing a voltage control dependent voltage source. Looking at the theoretical analysis on the left, we apply Kirchhoff voltage law around the clockwise loop by substituting Ohm's law where the controlling voltage equals the loop current times 1 ohm. We calculate a theoretical loop current of 15 amperes. This gives us a power dissipation of 1125 watts across the 5 ohm resistor. To validate these results, I built the circuit in a simulation tool as shown on the right. Notice that the current probe PR1 reads negative 5 amperes. This negative sign perfectly matches our hand calculation because the simulation probe detects current flowing from right to left, which is exactly opposite to our assumed clockwise current. The identical magnitude confirm that our theoretical math and formula derivation are 100% correct. Moving on to the next question, our objective is to determine the power absorbed by the 4 ohm resistor. On the left, our theoretical analysis simplifies the circuit step by step. Combining the series and parallel branches give a total resistance of 10 ohm. With a 20 volt source, this yields a total loop current of 2 ampere. Using current division, the current branches out equally resulting in exactly 1 ampere passing through the 4 ohm resistor, giving a theoretical power absorption of 4 watt. To validate this practically, the right side shows our virtual breadboard simulation. The DC power supply registered a total current output of exactly 2 ampere, validating our total resistance math. Furthermore, the digital multimeter in series with the target branch read 1000 mA, which converts precisely to 1 ampere. Substituting this simulated current into our power formula yields the same 4 watt result, perfectly verify our manual calculation. Moving on to our third simulation problem, we analyze a bridge network using mesh analysis. Because this circuit has three distinct closed loops, we establish three separate KVL equations for mesh 1, 2, and 3. By applying algebraic substitution step by step, we simplified the system of equations. We found that current I2 and I3 are equal, each carrying exactly half of the total mesh current I1. After substituting these relationships back into our primary equation, we successfully calculated the loop current I1 to be exactly 42.9 milliamperes. Now, let us move on to the next slide to verify this theoretical value using our simulation setup. Here, on a slide 10, we construct the exact bridge network using a Tinkercad breadboard simulation to validate our manual calculation. We apply the input source from our DC power supply, and as you can see, the digital multimeter placed directly in series with the mesh 1 branch registers an experimental current of exactly 42.9 mA. This perfect match between our rewritten hand calculation and the Tinkercad readout provides 100% confirmation that our mesh equation and its circuit analysis logic are entirely correct.
Assalamualaikum. So I'm back to present our simulation 4. So today I'm presenting the analysis of our target DC circuit. We will verify the output voltage VO using two distinct approaches: a manual calculation utilizing the superposition principle and a software-based verification using PSPice. Finally, we will compare and discuss the results. So to solve the by hand, we apply the superposition principle by evaluating one independent source at a time while deactivating the others. First, the 12 source alone contribute positive 2 volt. Second, the 2A source contribute positive 5 volt. Lastly, the 90 volt source acted heavily against the others, contributing negative 7.125 volt. Summing these individual components together give us final manual result of negative 125 millivolt. So next, we validate our mathematical model using a PSPice bias point simulation. We construct the circuit using ideal components, added the ground reference, and label our target nodes as A and B. The software instantly solves the network, giving a node voltage of 8.05 volt at node A and 8.175 volt at node B. Subtracting node B from node A confirm the differential output voltage is exactly negative 0.125 volt. So now, as we can see on these comparison slides, both methods achieve a flawless mesh with a 0% error rate. This perfect alignment validates our underlying circuits theories are completely identical to modern computer-aided design algorithms. While manual supervision offers deep insight into how a specific power source physically drives the branch, PS5 provide an instantaneous error-free verification of entire network simultaneously. So in conclusion, our linear circuit analysis is verified as completely accurate. This exercise demonstrates how hand calculations provide the engineering institution, while PSPice ensure commercial grade accuracy. That's all from me. Thank you.
Assalamualaikum and good day everyone. Today, I will present question 7, which require us to find the DC steady state voltage V using both manual calculation and PSPice simulation. After obtaining the results, we will compare them and discuss any differences. To determine the DC steady state voltage V, all capacitors were treated as open circuits and all inductors as short circuits. Using nodal analysis on the simplified circuit, the left branch current source of 4 mA and the middle current source of 1 mA were used to establish the node voltage. The voltage drop across the 21k ohm resistor and the 220k ohm resistor were calculated using Ohm's law resulting in a manual output voltage of 143V. The same circuit was then simulated using PSpice with a DC operating point analysis, and the output voltage obtained from the simulation was approximately 143V. Comparing both methods shows that the manual calculation and PSpice simulation produce the same result, giving a percentage error of 0%. This confirms that the theoretical analysis is correct and validates the accuracy of the simulation model.
For simulation 6, we analyzed a first-order RL transient circuit to find the inductor current, IT, for time greater than 0. Looking at the manual calculation on the left, we broke this down into two states. First, at t equal to 0, negative. The circuit is in a steady state where the inductor acts as a short circuit. By simplifying the resistor network, we determined that the 6 ampere source delivered a starting inductor current I of the 0 plus of exactly 2 amperes. Second, for t greater than 0, the switch open and isolate the source. The inductor now discharges its stored energy through the remaining resistors. By calculating the Thevenin resistance seen by the inductor, we found RTH to be 9 ohms, yielding an exponential decay rate, or 1/tau, of 18. This gives our final theoretical equation, which is IT equal to 2e power of negative 18t amperes. To validate this, the right side shows our transient simulation results. When the switch opens, the current immediately peaks at approximately 2 amperes and decays exponentially towards 0, precisely mirroring the behavior of our calculated equations. This flawless agreement confirms our transient litare analysis is entirely accurate.
Next, for question 15, we are given an AC circuit with a current source IS equal to 5 cos 10t plus 40 degree ampere. This circuit consists of a 4 ohm resistor, a 3 ohm resistor, a 0.2 Henry inductor and 0.1 farad capacitor. The objective is to determine the output current IO using phasor analysis. After obtaining the manual calculation result, the circuit is simulated in PSpice to verify the accuracy of the theoretical solution. Finally, both results are compared to evaluate the consistency between analytical calculations and simulation software. For the manual calculation, all circuit elements are converted into their impedance form. The inductor impedance is J2 ohms, while the capacitor impedance is negative J1 ohm. Using nodal analysis, the node voltages are obtained and the output current is calculated as IO equal to negative 0.181 plus J2.318A. Converting this value into polar form gives IO equal to 2.325 angle 94.46 degrees A. Therefore, the time domain expression of the output current is IOT equal to 2.325 cos 10t plus 94.96 degrees A. The same circuit was then simulated using PSpice. Then simulation produced an output current with a magnitude of approximately 2.3A and a phase angle close to 94 degrees. When comparing both results, the values are almost identical. The small difference is mainly due to rounding during the manual calculation and the higher numerical precision used by PSpice. Overall, the simulation confirms that the manual calculation is correct and validates the theoretical analysis.